Okay, cool. So rotational position, displacement, velocity, acceleration, mass, and force. No reason to stop now. Let's keep going. Oh, and energy. All right. So we have our rotational version of Newton's second law. Let's see what else we can do with that. Equals moment of inertia times the rate of change of omega. And I think you maybe can already guess where I'm headed. If the moment of inertia, if we bring it inside the derivative, we're talking about the rate of change of moment of inertia times omega. And that looks a lot like the fact that the net force is the rate of change of mass velocity. This is the analogous equation. The net rotational force, is the time derivative of rotational mass times rotational velocity, which makes me think that we could define this happily as, well, rotational momentum. I'll use a capital letter L for angular momentum. That is the quantum mechanics folks are to blame for that. This is the same L, by the way, that shows up when we are assigning letters to the orbitals of electrons. Quantum number L is this quantum number L. Okay, so angular momentum. If angular momentum changes, then that must be due to a net torque, which means we can now talk about a conservation law for angular momentum. If the net external torque can be shown to be 0, then delta L should be 0. The angular momentum should be constant over whatever interval this is true for. Excellent. Other ways to calculate angular momentum. We said that we can get to rotational force with R cross linear force. So here, if I want to get to rotational momentum, R cross linear momentum, and it turns out, yes, that's absolutely true. R cross P. That definition is going to turn out to be relevant when we talk about gravity, so it's a thing worth talking about. Cool, cool, cool. All right, so we've got a conservation law here. The other conservation law we talked about was the work energy theorem, and if we can show that the work done by non-conservative forces is 0. So let's start over. The work definition used to be force, well, I guess the integral of force dot displacement. So can we define an analogous thing? Torque dot d theta. And the answer is yes, why not? I mean, we made up this definition in the first place to match the definition of impulse. I don't see any reason why we can't talk about that. We could, by the way, talk about a rotational impulse as well if we wanted to. Why not? I don't have a ready to go symbol for that, but we could talk about a rotational impulse integral of torque dt. Why not? This is a perfectly good definition. In any situation we're talking about, the torque and the angular displacement are going to be in the same direction, or at least either parallel or anti-parallel. They're along the same axis. So this almost always reduces to the torque times delta theta. I guess the only time, well, almost always. If it doesn't reduce to that, it will, in our consideration, reduce to torque d theta. Possibly the torque is a function, we have to integrate it. That's maybe a thing. But the scalarness goes away if we let the if we talk about whether these two things are parallel or anti-parallel. So almost always the vector nature of this integral goes away for rotation. We don't need to worry about path integrals. We can just integrate. We can show that the work done is still equal to the change in kinetic energy. That's still true. I want to unpack, before we stop talking about chapter 10, there's a couple more things I want to do. I want to unpack our definition of torque. R cross F equals, well, it has a magnitude R F sine of the angle between those two things. And for clarity, I'm going to point the camera over here at the door. If we apply a force to the door swings. We cause an angular motion where there wasn't one before. So we must have exerted some torque, and the amount of torque that we exert, we can calculate asking about the distance to the point of the application of our force, that distance away from the axis around which the door is rotating, R. I'm pointing at the whiteboard like y'all can see it right now. Sorry. Multiply that by the magnitude of the force that we use. And we do have to also follow the rule for the cross product. We have to multiply by the sine of the angle between them. If we push in some weird angle not perpendicular to the face of the door, then we don't quite get the same oomph that we did when we pushed perpendicular to the radius vector, R. If the angle between them is 90 degrees, then we get the biggest rotational bang for our buck. If the angle is other than that, it swings a little bit more slowly because we've reduced the component of our force that is perpendicular to that action distance. It's this equation that helps explain the problem that happens when you push on the wrong side of a door. If we go up to a door and we push at the location of the hinge, almost nothing happens. Almost nothing happens because the action distance has dropped to almost zero. We gave the force, and a lot of force in that case, we gave the force that we are working with little tiny T-Rex arms. We can't get any leverage that way. we've taken away the action distances. As that goes to 0, the magnitude of the torque exerted goes to 0. And that sort of helps explain the conceptual justification for the torque equation. There's one more thing that I want to talk about in chapter 10, and then we're done.